This is going to show you how to calculate the final temperature of a mixture using the specific heat capacity equation. There's two questions to watch. The first question we'll look through is the Isaac physics question, G36. We'll look at part A. We are told we've got a mixture of water and paraffin, and we have to calculate the temperature of them once they've reached equilibrium when we've mixed them together. We've got 3.2 kilos of water at 83 degrees Celsius and 4.3 kilograms of paraffin at 18 degrees Celsius. We've got their specific heat capacities over here. We have to work out what the temperature of the mixture is when it comes to equilibrium. Because there is energy being transferred between the two of them, we've got the change in energy of the water will be equal to the change in energy of the paraffin. However, because the water was hotter and the water is cooling down, the water will lose energy. So the negative of the energy lost by the water will equal the positive energy that is gained by the paraffin. Substituting in the specific heat capacity for our changes in energy, we're going to have the negative of the mass of the water times the specific heat capacity of the water times the change in temperature of the water, which will be the final temperature, TF, the equilibrium temperature, minus the initial temperature of the water, I'm going to call TW, that's the temperature of the water to start with. And that will equal the change in energy of the paraffin, which will be the mass of the paraffin, times the specific heat capacity of the paraffin, times the change in temperature of the paraffin, which will be the final temperature the paraffin reaches, the equilibrium temperature, minus the initial temperature of the paraffin, which I'll call Tp. I'm now going to multiply out my brackets, and that will give me minus Mw Cw Tf, and then I'm going to have a minus times a minus here, so I'll have plus Mw Cw Tw. That will all equal, on the right hand side, multiplying out the brackets, I get the mass of the paraffin times the heat capacity of the paraffin times the final temperature minus Mp Cp Tp. The thing I want to calculate is Tf, and I've got a Tf here and a Tf here, so I'm going to move all my Tfs onto one side, everything that contains Tf onto one side. In fact, I'll move them to the right, and then everything else I'll move onto the left, so we'll get this. I will have Mw Cw Tw plus Mp Cp Tp, and then left on the right hand side I have my Tf terms. I'll have Mp Cp Tf plus Mw Cw Tf. This is the tricky part now. What we do is we factorise. On this right hand side I've got a Tf here and a Tf here, so I'm going to factorise Tf out the front and I will get this. The left hand side stays exactly the same, but now factorising Tf from the right hand side, I get Tf, open brackets, Mp Cp plus Mw Cw, close brackets. I can now rearrange to get Tf equals, which we'll do up here. We end up with Tf equals Mw Cw Tw plus Mp Cp Tp over Mp Cp plus Mw Cw. Looking back at all the values given to us, we can see that the mass of the water, Mw, was 3.2 kilograms. The mass of the paraffin, Mp, was 4.3 kilograms. The specific heat capacity of the water was 4,180. The specific heat capacity of the paraffin was 2,130. The initial temperature of the water was 83 degrees Celsius, and we can leave it in degrees Celsius for this equation. The initial temperature of the paraffin was 18 degrees Celsius. Try this out for yourselves. You should get a value of 56.58, which rounded to two significant figures. When you enter it into Isaac physics, you should get 57 degrees Celsius would be the equilibrium temperature of that mixture. This is a question from the lesson. It's when you put an iron block that is very hot in contact with a copper block that's quite a bit colder, and you want to see which temperature they reach when they reach thermal equilibrium. We start off doing the same thing as before, and this is the trick to get these questions right, is think about the change in energy. So there's going to be a change in energy of the iron, and there's going to be a change in energy of the copper. But which one will lose energy? Will it be the copper or the iron? Well, it will be the iron will lose energy because it was so much hotter to begin with. Because it was so much hotter, it's going to lose thermal energy and it's going to give that to the copper. So we put a minus sign in front of the change in energy for the iron. Then we substitute in our specific heat capacity equations for both sides and we get minus Mi Ci final temperature minus the initial temperature of iron will equal the change in energy of the copper, which will be the mass of the copper, Mc, times the specific heat capacity of the copper, Cc, times the change in temperature of the copper, which will be its final temperature, the equilibrium temperature, minus its initial temperature, the temperature of the copper initially. I now multiply out my brackets and I get minus Mi Ci Tf plus, because I have a minus and a minus, Mi Ci Ti equals Mc Cc Tf minus Mc Cc Tc. I'm now going to move all the terms with a Tf in it over to the right hand side, and all the terms that don't have a T in it, that don't have a Tf in it, which will be this term and this term, over to the left hand side. That leaves us with Mi Ci Ti plus Mc Cc Tc will equal Mc Cc Tf plus Mi Ci Tf. I'm now going to factorize Tf out of these two. This left-hand side will stay exactly the same, so I will end up with the same left-hand side as before, equal to Tf, so taking Tf out and then factorizing, I get MCCC plus MICI. Rearranging now for Tf, and what we get is MICI Ti plus MCCC Tc over MCCC plus MICI. Taking my values from the question, I have the mass of iron is 1 kilo, the mass of the copper is 1 kilo, the specific heat capacity of the iron is 420, the specific heat capacity of the copper is 385, the initial temperature of the iron is 600 degrees Celsius, and the initial temperature of the copper is 20 degrees Celsius. Taking all of these values and very carefully plugging them into this equation, and you should get an answer of 322.6 degrees Celsius, or as it was stated in the lesson, 323 degrees Celsius to the nearest 3 sig figs if you want to give it.